Hey everybody, welcome back to another round of astronomy. And yeah, let's get at it. Today, we're going to discuss the celestial sphere model, the model passed down to us from ancient Greece, describing the motion of the night sky. Now, one of the things I failed to mention in our Nature of Science video is that sometimes we'll use antiquated models simply because they help out with a particular aspect of conceptualization. So you ready? Yeah, here we go. We're going to have to start off with some terminology that will assist us throughout the rest of the course. So first of all, I'll mention the geographic poles. Those are the places on the Earth about which the Earth appears to rotate. You're probably more familiar with them. This is what you're thinking of when you refer to the North Pole or the South Pole. Now, when we're dealing with the celestial sphere, the night sky, remember that the Greeks thought that the night sky was simply a sphere surrounding the Earth on which all the stars were pasted. A physical glass sphere which stars are placed upon. Okay? So they needed a way of describing different locations on the celestial sphere. The first one is called the celestial poles, and they're related to our geographic poles. What you can do, take the geographic poles on the Earth, the North Pole, the South Pole, think of running a line through those two locations and out all the way out into space. Okay? Where that line intersects the celestial sphere, that is referred to as the celestial poles. So next up, this is why Polaris is so stinking important. Why I have put Polaris on your star charts is not because it is the brightest star in the night sky. Rather, it is because of location, location, location. Polaris, as seen from Earth, is basically on the North Celestial Pole. And because of that, Polaris is very helpful, for example, in finding which direction is north, right? If it sits on the North Celestial Pole, the North Celestial Pole is directly above geographic north. So if you can identify Polaris and walk towards it, you are basically walking north on the Earth. Now, the next thing that I'm going to give you terminology for are three planes that run through space. And they're going to be important for various reasons, some of it for navigation purposes, some of it just for referencing directions so that you know which way you need to look. Okay? So the first one, or the first terminology, or another term I'm going to give you, is the point in space directly above your head. Okay? That is referred to as zenith. Okay? So if you look straight up, right, you are looking towards zenith. If you're ever interested and you want to impress your friends on a Friday night, the location directly beneath your feet, towards the center of the Earth, that is referred to as nadir. Okay? So I don't tend to use nadir as much in this class. Zenith is the term that we're definitely going to need to use. Okay? Now, starting with these planes, okay, we will use a word to describe the plane, the line running from due north, due celestial north, to celestial south, passing through zenith. So take a moment, point north, okay, point south, directly opposite, and think about your two arms sweeping out a line until they meet directly overhead. That line running through the sky is called the meridian. Now, one thing I will point out to you right now is notice that for people located at different positions on the Earth, they will have a different zenith. Okay? And because they have a different zenith, if you're at different locations on the Earth, you have different zeniths, that means you're going to have different meridians. Incidentally, you're probably familiar with this term meridian already. No, not the prime meridian, capital P, capital M. Okay, that deals with geography, locations on the surface of the Earth. Okay, but you use this idea of meridian pretty much all the time. Okay, anytime you look at a clock. What do you mean? Let's get into some history. Okay? Before the invention of our fancy iPhones or our little fancy smartwatches, okay, how do we tell time? Yeah, it's based on the location of the sun in the sky. If the sun is to the east and really low on the horizon, it's morning. If the sun's to the west and low on the horizon, it's getting close to evening. So the location of the sun in the sky was historically what we used to tell time. Well, how do we know if it's in the morning? It has not yet crossed the meridian, right? Morning means that it's yet to cross the meridian. Now, I believe the Latin term for that was ante-meridian, A-N-T-E. Ante-meridian, meaning before the meridian. Of course, if it's in the afternoon, it has passed the meridian. And so what the terminology is, post-meridian. So anytime you look at a clock and you're asked your AM or PM, that M represents the meridian. That M is the abbreviation for meridian, the line running from due north to due south, passing directly overhead. Okay. Next up, I have 3 planes that I want to give you. Okay? And so we'll start off with this. Number 1, now that we have an idea about zenith, okay, the point in space directly above your head, I want you to be thinking about a location in space exactly perpendicular to zenith. Okay? So point to zenith. Okay? Now point to some place that's perpendicular to zenith. And perpendicular 90 degrees. Okay? So zenith directly overhead, 90 degrees, perpendicular, and now just pirouette, right? You can spin around once. Okay? Your hand has swept out what we refer to as the horizon. Okay? From an operational sense, the horizon is the plane through space that separates what you can see from what you can't see. Or alternatively, it is the plane through space that is perpendicular to an observer's zenith. Since different observers will have different zeniths, you will also have different horizons. So this depends on where you're located. That hopefully should make some sense. An observer down here in the southern hemisphere will have a different horizon, meaning that person will be able to see objects that a person in the northern hemisphere won't be able to see, and vice versa. Okay? So there's number 1. Number 2 deals again with the poles, the north celestial pole and the south celestial pole. You can think of the line connecting those 2 poles, and if I take a plane perpendicular to that, that is what we call the celestial plane. A different way to think about it is take the equator of the Earth and project it out onto the celestial sphere. That will be the celestial plane. Oftentimes, instead of seeing it as celestial plane, you will also see it as the equatorial plane. Okay? Those 2 terms are used interchangeably. Now notice the north celestial pole, the south celestial pole, and the equatorial plane, those do not depend on the observer's position on the Earth, right? Those are always the same for all observers, regardless of where you are. And that'll be particularly helpful when we want to specify locations in space. The third plane is the plane defined by the orbit of the Earth around the sun. Or if you're thinking about the Earth being stationary, it's defined by the orbit of the sun around the Earth. Okay? That plane that's swept out through space is called the ecliptic plane. Right? As it turns out, the Earth and most of the planets orbit in the ecliptic plane. So, if you're able to identify planets in the night sky, you can kind of draw a line through them and get an idea about where the ecliptic plane is. It's not by accident that I started off this lecture with a figure of several planets in the night sky. So that's it for terminology. Now we're at a position where we can sit and talk about the celestial sphere. So I call this the spaceship view. What I've got here is I've got a person, I've got the Earth in the center, I've got a person standing on it, and this grayed oval you'll see, I have indicated the horizon for that person. Okay? So this gray oval is supposed to indicate the portion of the sky that the person can see as versus the portion of the sky that the person can't see. Okay? Now, I've also labeled the north celestial sphere or pole, and I've put in the rotation axis of the Earth. Okay? Or similarly, if we think of the Earth as being stationary, like the ancient Greeks did, then this is the rotation axis of the celestial sphere, which I've drawn in white. Okay. Now, lastly, I'm just walking you through to try to give you a sense of what I'm trying to draw here. Lastly, I've pasted a couple of stars on the celestial sphere. And you can imagine as this bowl rotates around the Earth, those stars will complete a full orbit. So that's what those dashed lines, I mean for that to represent on the back side of the celestial sphere. The solid line is on the front side. So you can think of these stars as kind of sweeping out these paths. Okay? I call this the spaceship view. It's almost like you jumped in a spaceship, you flew out beyond the celestial sphere, you turned around and you're looking back at the planet. Now, the other one I have is, So the second one I have is the idea about, well, what does the sky look like for this person standing on the Earth? Okay? You have this giant glass sphere rotating around you. If you could paint out the tracks that the stars leave, then you would see all of these stars orbiting around the north celestial pole, or the south celestial pole if you're in the south. Okay? So I sometimes refer to this vantage point as the horizon view. You're sitting, you are the observer on the Earth, you have a horizon, and you're kind of envisioning what the sky would look like as the celestial sphere rotates. Okay? Now, sometimes I'll jump back and forth between these kind of two vantage points. So I want you to be a little bit familiar with them and kind of get used to kind of translating from the spaceship view over to the horizon view. Okay? Well, let's get some practice with the spaceship view. Go ahead. Which star will be located at zenith at some point in time for this observer? Take a minute, pause the video, give me an answer. You got it? Yeah, good. And so we have to remind ourselves, what does zenith mean? Zenith is the point directly above the person's head. Or if you prefer, the line perpendicular to the horizon. So I've got the horizon, I draw a line perpendicular to the horizon, I go straight up, and I get star A. Okay? Good, good, good. Next question for you. Let's go for another one. Right? Here we go. Which star or stars will set? Got it? Yeah, good, 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 good. So we should ask ourselves, in terms of some of the definitions or terminology that we have, what does it mean for a star to set? It means that it goes from above the horizon to below the horizon. Right? Same thing, if we have a star rising, it's going from beneath the horizon to above the horizon. So in this spaceship view, we need to get an idea about a star setting. So we look at A, and right away we can see A doesn't cross the horizon at all. So, okay, we're good there. Okay? How about B? Well, it gets closer and closer and closer. So here's due west, and then keeps closer, 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 closer. And you notice it never actually crosses the horizon. Okay, so not B. Okay, that means it must be star C. You see, as C comes down, 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 and right here, right there, our line is now crossing the horizon. So somewhere to the southwest, and for a little while it's below the horizon. Now we're on the backside of the celestial sphere, and somewhere to the northeast, it now comes up. So star C is the star that will set. Okay. And I guess I have another one here. Which star will never rise? Yeah, you got this one. You see, D never actually crosses the horizon at all. It always stays down below the horizon. And yes, there are stars that you will never be able to see standing here at Hanover, Indiana. There are some stars that will never cross your horizon, and therefore you'll never see them. The upshot is there are some stars that never cross the horizon, and you should always be able to see them. So the trade-off is there are some stars you'll never get to see, but the trade-off is that there are stars that you'll always get to see. Stars that you will always get to see for your given location are called circumpolar stars. The Big Dipper, for the continental United States, the Big Dipper is circumpolar. Polaris is circumpolar. And there are several other constellations that will be circumpolar when viewed from the continental United States. Okay? We'll talk about that a little bit more in the coming chapters. So I've missed a term, but I'll add it in right here. Okay, when we refer to altitude, okay, so not everyday language. Okay, usually you think the altitude of an airplane is distance above sea level in meters or in feet. Okay, that is not what we mean when we're talking about altitude in astronomy. In astronomy, altitude is the angular distance between the horizon and the object you're considering. So, question, which direction does this observer need to face in order to see star A at the lowest altitude, the closest to the horizon? Yeah, good, good, good. You see that, okay, well, over here, this big distance, okay, the horizon, smallest distance to the horizon, up here, okay, there's that. And you see this one's pretty big, okay? But as the celestial sphere rotates, A will eventually end up down here, and you see that that is a fairly small distance. So they'll have to look due north. If you look due north, A will sweep down, it'll get closer and closer and closer to the horizon, and that'll be its lowest altitude when you're facing north. And you notice B, star B, it even gets closer, right? Really small, really tiny. Good? The other thing I'll point out, when we're measuring altitude, we're talking about when the star is visible. Okay, good. Now we have a good model that came to us from the ancient Greece, the celestial sphere model, a conceptualization about the night sky. Glass sphere with stars pasted on it, and that model rotates around a stationary Earth. We call this a geocentric model. Geo, Earth, centric, center. Okay, so that's the idea of the entire celestial sphere. Now, because we have this model, it should be able to give us some predictions. So let's go through and think about what some of the predictions would be. For the geocentric model, the celestial sphere, I've got the Earth at the center, I've got the planets going around the Earth, and then this one represents the celestial sphere going all the way around. Okay? Question for you. What can you tell me about the direction that they move? Yeah, all same direction, right? If they're all pasted on the sphere and the sphere rotates one way, all of the objects should go the same direction. Another question for you. How about this? What can you tell me about the speed at which they move around? They should be constant or non-constant? Constant. Yeah. Good, good, good. When we look at the celestial sphere, we have some predictions. Objects should move the same direction at a constant speed, because that would correspond to them being pasted on the sphere and the sphere rotating. Okay? Good, 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 good. Okay. So recap. The celestial sphere model comes to us from ancient Greece, Aristotle, Plato, and it is what we call a geocentric model. The Earth at the center with objects moving around the Earth. Remember that the ancient Greeks thought that all stars were the same distance away. Okay, so that's kind of where they built this conceptualization from. Predictions that we can have from this model. All the stars should move at the same speed, and all the stars should move in the same direction. Okay? Now, as you're probably aware, or as I'm kind of hinting at here, is that we are going to now start looking for those observations, right? This prediction that we made is based solely off of our model. What we next need to do is experiment, go out and see if we observe the behavior that we expect from our model, okay? And of course, you're probably already familiar, we're going to see some problems. Okay? So I think that's it for this lecture. Be sure to write down your questions and send them to me or ask them in lecture or when we have some one-on-one time. I thank you for your attention. Keep up the good work. I'll see you next time.